Emma steps up to the plate, and let's see. She's holding her bat backwards because, okay, that's just, and that's her follow through.
Looks like they've been impaled.
Okay, can't wait for this to go on YouTube. Here's Emma following through after she swung and hit the ball. Okay, so on average, let's see, she hit it like 500 feet, which is only 300 feet further than the fence. So she hit two, this is a 2-run homer, and she was the only one at bat. I mean, nobody else was on base because she hit it over 2 fences. Okay, can we cut and start over again? So if I wanted to know how high it went after, let's say, 100 feet, I could figure that out based off the equation or the graph, and let's see, it went up, let's see, that's clearly 60 feet high at that point. And then the halfway point, if it's parabolic, 250, maybe the highest point is 75 feet, and so on. We can find any point along the way. We know the horizontal distance, that would be the input, and we can get the vertical distance by plugging in the equation or looking at the graph. Okay, that is not anything new. This is just a parabola, and we know horizontal distance and vertical distance. But if I asked you, where is the ball after 2 seconds, could you tell me that?
No.
You couldn't tell me where it's at after 1 second or 3 seconds. So we don't know when it is in that path. We just know that it follows that path. So parametric equations, a parameter is a variable. So parametric equations is adding another parameter or another variable. Okay? So not only is it going to be x and y, it is going to be t. So t's and x's and y's. And then we'll be able to know when t is 1, you can plug it in, and when t is 2, you can plug it in, and know when it is at certain locations. Okay? So parametric equations, I'll give you an example. It's going to be x equals t plus 1, and I'll say y equals t squared. And I also have to give you when the t's are happening, the interval in which so we're done with that. I'll move it off the screen here. Okay, so here's my set of parametric equations. I've got x in terms of t, and I've got y in terms of t, and I have my time interval from 0 to 2. So if I was going to just make a table, it's no longer an xy table, it is a txy table. My first t value, what's my last t value? 2. So I'm going to go from 0 to 2. Very good. Number 1 and 2. So when t is 0, what is x equal to? 1. Very good. You can plug 0 in for t, and I get x equals 0 plus 1, which is 1, comma. If I plug 0 in for the y equation, I get 0. Okay, 1/2 plus 1 is 3/2, comma, 1/2 squared is 1/4. 1 plus 1 is 2. 1 squared is 1. 3/2 plus 1, so 3/2 plus 2/2 is 5/2, comma, 3/2 squared is 9/4. And 2 plus 1 is 3, and 2 squared is 4. Are you with me? Okay, so we have all of those points. We have 5 ordered pairs. So if I was going to graph them, you need graph paper, which I found. Thank you very much. So life goes on because I have graph paper. My first point is at 1, 0, right there. And then 3/2, 1/4, so 1/2, 1/4, we'll call it right there. 2, 1, and I'll go 3, 4. I guess 5/2, 9/4, like right there. Did I draw myself a straight line? So if I connect them, this is what it would look like. Okay, so there are two differences with parametric graphs. Two differences. One difference is you may have initial points and terminal points. In this case, we do have an initial point. That's my initial right there at 2 comma or 1 comma 0. This right here is your initial. And terminal means the end. This right here is your terminal point. And here's my terminal right there. Terminal. Okay, so that's one difference. You might have initial points and terminal points. And I say might have because in this case, I'm starting at t equals 0 and going to t equal to 2. If I went from negative infinity to infinity, that means this is just going to keep on going that way, and then this is going to go whatever direction is going forever in that direction. You will not have initial and terminal points for this problem, for that set of parametrics, if you go from negative infinity to infinity. I'm trying to keep the with there. It is lined up. Okay, the second thing. So you might have initial terminal points. You also need to demonstrate what direction it is going. I know as time progressed, that's when time is 0, that's when time is 2, it was going this direction. When you graph parametrics, you have to include arrows indicating which direction it's traveling. All right, so another thing we need to talk about is finding rectangular equations. I'm going to have to slide that away. So rectangular equations. So how to find. We'll give you two ways. The first way always works, but there's an easier second way for some types of problems. So, first way, solve for t in the x equation, plug into the y equation. Okay, so we have x equals t plus 1, and I have y equals t squared. I said solve for t in the x equation. Well, all I have to do is subtract 1, so x minus 1 equals t. Are you with me? I solved for t. And so we have y equals x minus 1 squared. This right here is my rectangular equation for this set of parametrics. Do you see any t's in that equation? They are eliminated. Okay, rectangular equations only have x's and y's. Parametrics have the t. So that's why we eliminated parabola. Parameter. I got confused with my 4-syllable p words, I guess. Parabola, parameter. Okay, they both are 4 syllables. Okay, so we don't have a t. We're just left with our rectangular equation. So how does that relate to the graph? If I graphed this right here, what kind of a shape is it?
A line.
Don't say parameter. It's a parabola. Does it open up or down? Very good. What's the vertex of that parabola?
1, 0.
You've learned so much this year. Very good. 1, 0. So, if I was going to graph that, it looks like this. Notice, my parametric, the red one, is just part of the rectangular. It's a chunk of it. It's when time is 0 to time is 2, or it goes from 1, 0 to 3, 4. Okay, the rectangular is used to demonstrate what the path will be for the parametrics. Sometimes the parametric graph uses the entire rectangular graph. If it goes from negative infinity to infinity for this one, it would be the entire parabola. Then the only difference would be that you demonstrate that it's going to the right, you'd have the arrows. Okay, so that's how you can find the rectangular equation. Here, why don't you try one? You don't have to graph. I'm just going to have you find a rectangular equation by eliminating the P word. X is clearly going to be 3t, and y is the square root of t plus 4. This stuff doesn't matter for you. Okay, take a minute and see if you can give me the rectangular equation. All right, so all we have to do is solve for t in the x equation, so we're going to divide by 3, so x over 3 equals t. Plug that in. Y equals the square root of x over 3 plus 4. Right? Okay. So that's how you would normally solve for the rectangular equation, and then you could graph this, and then you would know what path a parametric equation would be taking. Okay, that's one way of doing that. If you're given x equals 5 sine t, and you're given y equals, I'll say 4, sorry, x equals 4 sine t, and y equals 2 cosine t. And I'm going to say from 0 to 2 pi. If you're given this, and you wanted to find the rectangular equation, you could solve for t, but it would involve an inverse sine, and then you'd plug that into the y equation. You'd be finding the cosine of the inverse sine of x over 4, which we did this year. We draw our triangle, and you're trying to find what angle has a sine of x over 4. You do that and then figure out the cosine of it. I'm not going to make you do that right now, although we can talk about that tomorrow if we want to. I think it's fun. A shortcut. Recognize that sines and cosines are involved. So we ask Carl, how are sine and cosine involved? Well, the sine squared of anything plus the cosine squared of the same thing is always equal to 1. Very good. Okay, that's a thing. So what we can do is we can solve for sine right here. Sine of t is equal to x over 4, and we can solve for cosine t. Cosine t equals y over 2. Well, we know that the sine squared of t plus the cosine squared of t is equal to 1. Well, what's sine t equal to? Remember, this is the same as the sine of t, the quantity squared plus cosine t squared equals 1. That's the same thing. So what is sine t equal to in this problem? X over 4. So I'm going to plug that in. X over 4 squared plus, what's cosine t equal to? Y over 2 squared must equal 1. If I clean that up a little bit, what kind of shape do I have? Did you just say ellipse?
Yeah.
You're so smart. It's an ellipse. I know it's not a parabola because why?
It's opposite.
They're both being squared. I know it's not a hyperbola because why? Because we're at thanks to the demonstration. Charlotte's back there going plus. So I know it's an ellipse because these two numbers are different. What's my A?
4.
A is 4. My B is 2. So I'll make my little sketch here. Center is where? right there. The center's right there. So B, 4, 1, 2, 3, 4, up 1, 2, 3, 4, up 2, down 2. I have my ellipse with a major axis of 8, minor axis of 4. All right, so this right here, parametric equation, this will give us an ellipse. Now we want to go from 0 to 2 pi. It's time to grab our calculators and let them do some work. So, graphing calculator, you should be in parametric mode. You may still be in polar mode. So mode, gone are the days that we use function. Now we're doing parametric. Okay, go ahead and enter those two equations. So hit y equals, and you notice that it's both x and y in terms of t. My x is 4 sine t. That's not a 4. And my y is 2 cosine t. That looks like it's kind of the default. So I'm going to hit graph and Shazam. I don't see anything. Wait, it's going. No. Well, I'm going to hit enter and go to my... All right, so I'm in degrees. Shame on me. I'm going to go to radians and try that again. How embarrassing. Isn't that gorgeous? Now, if we were going to graph this ellipse, we know that it's this shape. Calculator even said that. Because if you go to window, it did go from 0 to 2 pi, which was specified in this problem, from 0 to 2 pi. But I am not done until I demonstrate which direction it's going. Which way did the calculator draw it? Clockwise or counterclockwise? Did it go clockwise or counterclockwise? Okay, we weren't paying attention. So I'm going to clear drawing. You can go to draw right here, hit second draw. I can clear drawing, and then it draws it again. Okay, so make sure we draw our arrows. All right, remember, what's my initial point right here? Does this have an initial point? Yes, it starts at 0. What is my initial point? If I plug 0 in for the x equation, what do I get? The sine of 0 is what? 0. 0 times 4 is 0, yes. The cosine of 0 is, you're on a roll. You're not anymore. What's the cosine of 0? 1 times 2 is 2. So 0, 2, there's my initial point right there. And we know it went all the way around and ended right there. So it has all those points. Your calculator showed that it goes that direction. Change your T max to just pi now. Go up to window and change your T max to pi. What happens? T max is just pi now. All right, so it goes until it gets to pi and then it stops. It only does half of an ellipse. Yep. If we wanted to, we could go back and we could graph our original parametric equation of the calculator, specifying the T min, T max. It'll do it for us. All right. I think that is all. So there's two ways of finding the rectangular equation. The first way is solve for t in the x equation, plug it in the y equation. The second is when you have to use Pythagorean identities. So there's three of them. There's sine squared plus cosine squared equals 1. There's one involving tangent and secant, and then the third one, cosecant and cotangent.